This tutorial video is going to be discussing molarity and how to actually work through some molarity problems. And we had the experience in the laboratory of recognizing that molarity is essentially concentration. So the term molarity is usually used in chemistry to describe a concentration of a solution. So here I have an example of various solutions that have food coloring in them, and I'd like you to guess which one has the highest molarity. If you guessed the chemical or the beaker that is furthest to the left, you are correct. This has the highest molarity. Where on the other hand, we have this beaker that has the lowest molarity. And the beakers in between have a varying degree of molarity. So as you saw in that image before, molarity is determined by the ratio of solute, in other words, the moles of a chemical, and how much solvent or water is included in this. And here below you have an example where we have what looks like the same concentration of this blue dye. All of the colors look about the same shade of blue. But you notice that some of these beakers or containers have more volume and some have less volume, yet the concentration is the same. And so that means that in these beakers, the amount of chemical varies so that you have a different not only a different amount of chemical, but also a different volume of water. But if you were to look at the ratio is the same for all three of them. And that's why they have that same color. Whereas in this example here is that while we do have varying volumes, let's assume that they're more or less all the same volume of liquid. Clearly, some of these solutions have more chemical in them than others, even though more or less they're the same volume. So what does that mean mathematically? We were talking about that molarity is the ratio of the solute to the solvent, in other words, of how much chemical you have dissolved in water. And we can show that in a mathematical expression of moles over volume. And you saw that in the lab where you recognized the more chemical you put into the container while still keeping the volume the same, the stronger the concentration, or we can say the greater the molarity. And we also saw in the lab that if you put a certain amount of chemical in there, and if you kept on adding more and more and more water, the less concentrated that solution became. We can call that the more dilute the solution came. So it's less concentrated, and we say that it has lower molarity or less molarity. So it all has to do with that ratio of the amount of chemical you put in compared to the amount of water you put in. Now, when we are dealing with molarity, we're specifically looking at the amount of chemical put in, not the mass of the chemical. And so a couple of notes is that we need to make certain that we convert our grams into moles. Remember, moles are the amount. So in 1 mole, it's 6.02 times 10 to the 23rd atoms. And we want to make sure that we look at the ratio of amount, not mass. Okay, so all of our calculations are going to be when using molarity in moles, not grams. So we need to convert those grams into moles. You'll also notice that the volume is in liters. And most of the experiments we'll be doing in the classroom or that are done in a lab are actually measured in milliliters because they're quantities that are much easier to work with. And so very often you're going to be given a question where you have milliliters of solution and you just need to make certain that you convert it into liters. And just a reminder, 1,000 milliliters are in 1 liter, okay? So let's go through some of these examples. I have a scenario where a student places 0.53 moles of copper 2 nitrate in a beaker and fills the container with water to the 700 milliliter mark. What is the molarity of the solution? So what I always like to do is always draw things out for myself. So here I have a beaker. There we are. I'm told that I have placed in there 0.35 moles. All right, now we've got this copper 2 nitrate, and this is where we're now going to be reminding ourselves of how to write chemical formulas. Just a reminder that 2, Roman numeral 2 for copper tells us we have 2 valence electrons. And then nitrate, that ATE ending, tells me that it's polyatomic. So when I look at my polyatomic chart, I see that nitrate is NO3 and that nitrate has a -1 charge, which means that I'm going to have 7 valence electrons. This copper wants to get rid of 2, nitrate wants to gain 1. So at this point, the nitrate got its 8 valence electrons that it wants, but this copper hasn't lost its 2 valence electrons, so it wants 1 more nitrate. And so we're going to go ahead and draw 1 more nitrate on here. And there we are. That means that copper nitrate, for every 1 copper 2, you need to have 2 nitrates. So we're going to write the chemical formula as CuNO3 2. We're going to be using that throughout our equation. So we'll continue to use the same chemical over and over again. So we have placed 0.35 moles of CuNO3 and I mentioned that the volume was going to be 700 milliliters. That's how much liquid we have in here. Now, a couple of things, as I had mentioned in my note. 1, convert variables to moles, liters, or molarity. Okay, we'll leave that one out actually. So when I look at this here, I have my amount of solute in moles, so that's good. But I have here 700 milliliters. I need to convert that milliliters into liters. And remember, I have 1 liter equaling 1,000 milliliters. That means I can create a conversion factor. I either have 1 liter over 1,000 milliliters, or I have 1,000 milliliters over 1 liter. This is what we've been doing with conversion factors all along. So let's take our given. Our given is 700 milliliters. Whatever unit I have here, I instantly place on the bottom. Now I look at my conversion factor, which one has the milliliters on the bottom? It's this one right here. And so I place 1,000 milliliters over 1 liter on top. These cancel out. And my answer is 0.7 liters. So the second task is I need to figure out, using my equation, what my molarity is. So let's go ahead and remind ourselves, use molarity equation. What exactly the molarity equation is. So from that slide before, we said that molarity equals moles over liters. So we have our moles here and we have our liters here. So let's go ahead and insert it. 0.35 moles of CuNO3 over 0.7 liters. And that means that our answer is going to be 0.5, and we say with this M, 0.5 molar solution. We don't call it molarity solution. We actually use the term molar. So it is a 0.5 molar CuNO3 solution. Let's try the next one. All right, for the next one, we are told that we have 0.2 moles of copper 2 nitrate. Just a reminder that that is CuNO3. And it's placed in a beaker, and you want to make 1.5 molar solution. How much volume do you need to have? So the first thing we need to do is check units. Remember, I was saying, are these units in moles or, if appropriate, liter? And so it is. So that means that we can plug these in pretty much as is. So in this case, I'm going to use my equation. So the equation is, just a reminder, molarity equals moles over liters. All right, so in that case, what am I going to need right now is I'm going to plug it in. I have 1.5 molar solution equals, then I'm going to take these moles, 0.2 moles CuNO3, and then L is my unknown. We'll go ahead and put a question mark here. So that means we need to isolate that variable. What we can do is we can do the cross multiplication so that you have 1.5 molar solution with our question mark L. Here we go. Equals 0.5 molar CuNO3. Remember, this is our unknown. We want to get it all by itself. So I'm going to divide this side by 1.5 molar, and I'm going to divide this side by 1.5 molar. These cancel out, and my answer is going to be 0.13 liters of solution is what I need to have. But let's say, for example, 0.13 liters is always a struggle to measure in a lab. Perhaps I want to have it in milliliters. What I can do is I convert that into milliliters. So I take 0.13 liters. I use my conversion factor. Remember, 1 liter equals 1,000 milliliters. So I can put 1 liter on the bottom, 1,000 milliliters on the top, and I get the answer of 130 milliliters of solution. That means that I'm putting 0.2 moles of copper nitrate in there, and I need to fill it up to the 130 milliliter mark to get that 1.5 molar solution. Now this is a scenario that is very common in the lab. Let's go ahead and approach this one. This is where I ask you to make a certain concentration of solution. So I place 17 grams of copper 2 nitrate in a beaker, and then I fill the beaker to the 50 milliliter mark. Okay, so you notice I now have, I'm going to check my units. And you notice that in checking my units, do you have moles, liters? And the answer is I don't. So the first thing I need to do here is do a conversion. And this is what you've been working on all along. You have 17 grams of CuNO3. I need to convert that into moles. And so what do? Is I use my molar mass. All right, so with that said, I have 1 mole of Cu. So that's going to have a mass of 63.55 grams. That's number 29 on the periodic table. Then I have 2 moles of nitrogen. That's going to be 14.01 times 2. And then remember I have 6 moles of oxygen. Each oxygen is 16.00 grams, and I'm going to multiply that by 6 so that I have 1 mole of CuNO3 having a mass of 187.57 grams. Now, why is it that we're doing that? Because remember, this value here, I need to get into moles. Okay, so let's go ahead and do a gram to mole conversion, like we've been seeing and doing all along. And remember, for these conversion factors, I either can write 1 mole CuNO3 over 187.57 grams CuNO3, or I can do the reverse, where I put 187.57 grams CuNO3 on top and 1 mole CuNO3 on the bottom. So I have grams of CuNO3. I'm going to put 187.57 over 1 mole CuNO, and I know that's going off on the page. And my answer is that I have, in this case, 0.091 moles. So let me put a box around that. Okay, the next thing that I know that I have, I'll change colors here, is that I have 50 milliliters of solution, and I need to convert that into liters. So I know that 1,000 milliliters is 1 liter, and that volume is going to be 0.050 liters. So last piece in all of this calculation is putting it into my molarity equation. Remember, molarity is moles over liters. I have my chemical in moles now. It's 0.091 moles. And I have the volume of 0.050 liters. That's my molarity, and the answer works out to be 1.02 molar solution of CuNO3. All right, last one, and that is where you have a 0.2 molar solution and, you place 0.2 moles of copper 2 nitrate in a beaker and want to make 1.5 molar solution. You check your units. And my units look good. It looks like I have moles and molarity. And now insert into equation. All right, and in this case, I'm going to restate my molarity equation. And so that means I have 1.5 molar solution. I'm going to have 0.2 moles of CuNO3 over liters. So we've seen something like this before. And the answer of this one here is, oh, I see. We've done this one before, so we're actually pretty good. Well, I'm going to skip that one. All right, let's try this one instead. So here I have a situation where I am told that I have 50 milliliters of 1.5 molar copper 2 nitrate solution. How many moles of copper 2 nitrate does it contain? How many grams? Okay, so I check for units. And I recognize that 50 milliliters needs to be converted into liters. Again, 1,000 milliliters for every 1 liter. And so that means I have 0.050 liters. And now we can plug it into the equation. Okay, so insert into equation. We have molarity, moles over liters. And I plug it into 1.5 molar solution. And I have, in this case, 0.050 liters. And this is my unknown moles. So I can cross multiply these two together algebraically. So I have 1.5 molar times 0.50 liters to get an answer of 0.075 moles of CuNO32. So that gives us our first answer, how many moles, but then they're asking us to convert this into grams, and so now I do a mole to gram conversion. And in this case, I again look at my conversion factor. I know that 1 mole of CuNO32 has a mass of 187.57 grams. Remember, we solved that originally. So I make sure that moles are on the bottom here. And I've got my mass on top. And my answer for this one is going to be 14.07 grams of CuNO32. Okay, so that means that I have to put 14.07 grams of my copper nitrate into the beaker and then fill it up to 50 milliliters.